Hello everyone, I hope you're doing well. So in the previous class we learned about signals, and we established that signals are essentially anything that can be transmitted, or rather, if shown to another person, they're able to decode that or interpret that as anything. Like we said, a wave is a signal, like a hi may mean a bye, or hi, how are you? So that's essentially a signal. But we also say that in today's lesson, we're going to look at a spatial component that is very important to in building the computers, that is called a transistor. So yeah, this is what we're gonna study today, and also touch a bit on logic gates. So what is a transistor? A transistor is a semiconductor device used to amplify or switch electric signals and power. It is one of the basic building blocks of modern electronics. It is composed of a semiconductor material, usually with at least three terminals for connection to an electric circuit. So this is what Wikipedia tells us. But remember, in our previous class, we had this circuit, and we also studied about components, and we can see that we touched about some of these components. So a transistor is this 3-pin component that we're talking about. A transistor is essentially this kind of switch, just a normal switch, but then it's spatial in such a way that you're able to control it using electric signals. And I think we're gonna see it as we continue looking at this class. So but before that, we have to understand, or rather just touch a bit on semiconductors. So a semiconductor, we basically know that we have various kinds of materials. We can have materials that are able to conduct electricity. These are like copper wire. Basically, most of the metallic things are able to conduct electricity easily. And we also have other materials that are not able to, or rather, they have, they essentially, it's hard for them to conduct electricity. They're bad conductors. That's the word I'm looking for. Poor conductors, like, let's say, the insulator thing, rubber thing used around wires to insulate wires. That is a bad conductor. That's why it's used to insulate. And we also have things like, let's say, wood, plastic is also not a good conductor of electricity. So we have established that conductors are good conductors. We have good conductors of electricity and bad conductors of electricity. So a semiconductor material is a material that sits between. It works in such a way that it doesn't really conduct in its natural way, but if you modify it in some way by probably heating it up, that modifies it. You can have applying a voltage. So by putting this semiconductor material in an electric circuit whereby electrons flow through it, we can be able to manipulate the conductor, this material that is semiconductor, to act as a conductor. So by us having that control, we're able to switch on and off the conductivity of this material at will. So this is a very important thing in computing, since we are able to control if the material or the thing is able to transmit electricity or not. And as we looked in our previous class, it's important for us to do this, to encode our messages like the way we did in the signals, the way the operator in who was hitting the device, it's called the telegraph device, to encode some data. He was doing it using some pattern. So in our case, our pattern is going to be a pattern of on and off. That's all we need to build a computer, a digital computer. So we can look more about these transistors. We have PNP transistor. We have NPN transistors. We also have MOSFETs. We also have other kinds of transistors that are really, I'm sure you've heard of this, that material like, okay, not a material, the CPU, like let's say an Intel kind of CPU, is made up of billions and billions of transistors. So they're not really these kinds of transistors, but they work exactly as these kinds of transistors. So this is just like a simple component that's gonna show us how the actual transistors that are built in to build a CPU or other kinds of circuits in a computer, they're built. So in this case, we're gonna look at this, and we can see that a transistor usually has 3 pins. We have, this one is labeled as 1, 2, 3. Essentially, we have one as the emitter. No, I don't like this order. We have the collector. Yeah, I don't like this. Let's use this. We have the collector, which is essentially this. I think this is inverted, I don't know. But we have a collector, we have an emitter, and we have a base. Think of this as part of the circuit. So let me see. Let's say we have our circuits, electrons flowing from this side. They come over here, they move over here, and then move over here. Let me undo that. Let's say we have electrons flowing this way, then flows this way, and out to complete the circuit. And this goes to probably the this is, let's say, the negative terminal, and this is the positive terminal. So for this device, we have, for electrons to flow, we have to complete this circuit. So let's say this transistor is part of the circuit. It's passing through the first pin and to the third pin. And then we have the center pin as the control pin, which is called the base pin. And it's here, it's denoted by this P. So this, essentially this circuit, if we don't have a voltage over here, this circuit, we can consider it as, it's like the wire is cut over here. It's like the wire does not exist. So there's a gap. in between here. And if we apply a current over here, if we apply a voltage over here on the base, it somehow is able to connect this over here, and the circuit is complete. You can go and look at how the transistor works from a chemistry perspective. It's really interesting how it works, but from what we have to understand is that we have 3 pins. The first pin is the inlet, the last pin is the outlet, but the inlet and outlet cannot connect unless we have a voltage on this center control pin. So that essentially builds our transistor, which is basically a switch, just a normal switch, but controlled using electric signals. So, and it turns out that by just having these transistors arranged in a particular way, we are able to build a computer. So, I guess in our lesson today, we're gonna do a bit of history before we understand how we're able to use this principle of having just a simple, okay, it's not simple, but such a circuit to construct a computer and be able to do operations on it, play games on it, among other things, or even run AI models on it. So before that, we need to understand Boolean algebra, or rather just touch on it, a bit on it. So we have Boolean algebra. It was invented by a guy called George Boole. So what is Boolean algebra? Okay, it says that Boole used axioms. Axioms are statements that are taken to be true to demonstrate that logical reasoning could be treated as a mathematical calculus whereby symbols represent class and logical operations correspond to algebra manipulations, thereby integrating logic and probability into unified mathematics. So George Boole essentially was, I guess, he was a philosopher who wanted, who was really intrigued about reasoning, or rather how we think, or rather, what's the word? How we are able to, just communicate ideas and shape narratives. So, essentially, so he took away, he took our thinking process, and he said that our thinking process, or rather what everything we do in our brain, or rather in our mind, can be represented in form of mathematics and operated on. So that's logic. When you're trying to think, you're doing logical things like expressions, like if this, then this, then this, then this. So essentially, that's what our minds do. That's what our brains do. And he was able to construct a whole branch of mathematics that's able to look at these logical statements and operate them like mathematics and be able to come up with outcomes. He's really an interesting guy. You should go and look at more about George Boole and why Boolean algebra is very important to computing. So this is what is important. Just go and look at it. And we also have another person called Claude Shannon. So after George Boole came up with this branch of mathematics, there was this guy called Claude Shannon. We're told that he was a polymath, and was a mathematician, also an electrical engineer, a computer scientist, a cryptographer, an inventor, known as the father of information, and we'll understand why he's known as the father of information, the information age. We're told that Shannon was the first to describe the use of Boolean algebra, essentially to Boolean algebra, essential to all digital electronic circuits, and helped unfold the field of artificial intelligence. So I remember we had this guy. This guy looked at logic and how we think and said that we can convert this, or rather represent this, everything that we use our minds to represent this as like mathematics, which is a universal language and easy to understand and predict, right? So he did that. This is in the I guess 1800s. George Boole did that. Then later, close to 100 years later, about 83 years later, Claude Shannon, also a mathematician who was dealing with information and a lot of other things, he looked at these invention that was built long ago by George Boole, and thought to himself that this is the same as this can be represented as digital electronics, and it can be used to rather to represent information. That was at least the idea when he was starting. So we're told that George Boole in 1854, he gave us the laws of logic, truth, false, and or not, as a branch of mathematics, with no computers in mind at all. He thought he was just formalizing the human reasoning. And then years later, 83 years later, in 1937, Claude Shannon, he realized that electrical switches, they obey those exact same laws that were stated by George Boole in Boolean logic, since we have electricity as either on and off. And Boole, he gave us these rules. Boole gave us the rules, and Shannon gave us the machine, which is the computer. So he saw that this electrical circuit, it kind of works the same as the Boolean, it obeys the Boolean algebra exactly, or rather the Boolean logic exactly as it was stated by that branch of mathematics. So instead of people trying to guess how electrical circuits were going to be used, you could just have an equation of how the electrical circuit would be, and just follow that logical expression to build a circuit that does some logic rather. And due to that, we had now something we call and then something we call logical circuits and logic gates were born. So we're gonna look at that, but before we go ahead with that, we're gonna see today's lesson is going to be it's going to be a bit interactive. So we're gonna see how we're gonna see a transistor. So let's see. So as we can see in front of me, we have this is a breadboard. We have a simple circuit. We're gonna look at simple circuits to understand what we are talking about. So this is a transistor. It looks like this. I don't know. I hope we can see it. Yeah, looks like this. Looks like this. We have, this one does not have its long legs, but this one has. We have another one over here which has the long legs, but let's just work with this. So we see that we have 3 legs on this transistor. We have the first one, which is the collector. This one receives the it's part of the circuit, receives the signal. This one outputs the signal, and over here, this is the control pin. It's gonna, if we apply a signal over here, it's going to allow electrons to flow from here, or rather electrical current to flow from this to this. And knowing that, we're gonna look at a simple circuit. So over here we have a simple circuit which is called, this is a NOT gate, essentially, or rather an inverter. What an inverter is from the word, something that if you give it something, remember we're dealing with logical statement, which is true or false. So if you give it true, it gives you back false, and if you give it false, it gives you back true. And true and false in computation, it's 0 and 1. That's the representation. So in this circuit, we're gonna use this button as our input. So currently we're not pressing it. So, and if we're not pressing it, that's a 0. And as we can see, we are not pressing it, and the light is giving us, the output is 1, or rather true. And if we press this, it's supposed to invert. So the circuit is supposed to go off. The LED is supposed to go off. And so if I click here, the LED goes off. And if I release, it comes back on. And if I click again, it goes off. It's doing the inverse, assuming this is the input, and clicking down is inputting, it's allowing the current. It's not even assuming, it's by clicking this, I'm completing the circuit. And by completing the circuit, weirdly enough, the LED does not light up. And by releasing, it does light up. So yeah, it's kind of an inverter, and this is very important. It's called a NOT gate. And essentially, these few gates that we're talking about today, they're parts of circuits that if they are arranged in a particular way, they are able to do interesting things. Uh, yeah, like build a computer and do mathematics and other things. So yeah, but before that, let's look at uh, for better understanding, let's look at a simulation of the same circuit in Circuit.js. So as we can see, our original circuit had was made up of an LED. This is a resistor, and this is the battery, and this is the switch. So currently, this is just a normal circuit. If the circuit is open, we see that electrons do not flow, and therefore the LED does not light up. And if I close the circuit, we can see the flow of electrons. This is I noticed that in electronics we have different representations. We said that electrons flow from the negative terminal, which is this short thingy, and then we have this other tall terminal. This is the positive, and we know that we have different representation of using the circuits. Electrons should, as we can see on this circuit, electrons seem to kind of flow from this positive to negative, but that's not what we talked about. We say that electrons flow from negative to the positive. So in my research, I saw that we have different representations of these electrical circuits. We have the electron flow, which will show the electrons flowing from this opposite side. So it will essentially go on the opposite direction. And we have, this is called conventional current, which essentially is what is mostly used in electronic circuits representation. So whereby we have everything flowing from this positive terminal to the negative. That's why we have our batteries labeled plus on the positive and minus on the negative, but that does not really affect anything. So just get the difference. So for now, this is the electrical current. If we see these dot things, we're talking about the electrical current flow. So this is a normal circuit. So let's look at an interesting circuit, the same circuit that we've just seen right now, which is the NOT gate, or rather the inverter. And yeah, let's see. So this is the structure of the NOT gate. And as we can see right now, the circuit is open and the LED is on. Same way as we saw on the physical breadboard. And if we close the circuit, okay, this one uses a hold. Let me just replace it. Let me replace it with just a normal switch. Yeah, and we can see that now the current does not flow. The circuit is closed. Now the LED does not light up. And if I open the circuit, the LED lights up. So this is an inverter kind of circuit. You can see the if the circuit is open, as we can follow this green, the transistor over here, the base of the transistor does not have any it's not activated. So that means that the circuit does not flow through this transistor to over here, but it flows over here, and it has an alternative route to use to light the LED. And if I close the circuit, now as we know, electricity kind of uses, I guess, the path of least resistance. And as we can see over here, we have this resistor, but if we come over here, we have this junction whereby we have an LED. An LED is essentially any electrical component. Let's go back and see this. Back to our presentation, we can see that as we talked about, any of these components that sit over here, any of these components, all these, essentially I would say that every element has some kind of resistance. So any component, electrical component, has some resistance, and it utilizes this resistance, or rather this resistance is used to represent, I don't know how to put it, but yeah, the electrical current is utilized by an electrical component. For it to work, it has to have some resistance. Like as we looked at this filament bulb, we saw that if electrons flow over here and they reach over here, for them to light up this bulb, the old kind of bulbs, they had to knock the protons over and excite them to produce light and heat. So that's essentially a resistor, and this is an electrical component. So it's the same for all kinds of components. It's the same for all kinds of components. And as we can see in this circuit, this same LED has some kind of resistance. So if the electrical current flows over here, if you evaluate this path and this path has some resistance. So the electrical the electrons are not going to flow through this side, since we have, or rather the electrical charge is not going to go this way. It's gonna follow this route, and therefore on its path it's not gonna meet this and closes that. And if we open this circuit, essentially now this the current flows this way, comes over here to this junction, sees a route this way, and sees another route this way, but this route does not lead to anywhere since the base is not activated. Therefore, this is not a circuit. Since it's not a circuit, has to be complete, but this terminates over here, and so it has no choice but to use this path. And so by using this path, goes through the LEDs, and the LEDs uses that electrical charge, electrical current to produce light. And that's how we have the LED lighting up. And essentially that's the NOT gate. So right now we are studying this in electrical to understand how these simple gates are going to be they are constructed fundamentally, but In our other classes, we're gonna look at how they are used, assuming that we understand this, and how they are combined in interesting ways to build a computer. So let's look at another circuit. Other than NOT gate, we also have a circuit called as an AND gate. As from the name, an AND gate is essentially looking at two statements, or rather two inputs, and comparing them, and only if both statements are true, if statement A and statement B, if both of them are true, then the output should be true. Okay, so that's how it works. And as we can see on this circuit, we have the switch. Consider it, this switch as inputs. Right now it's pressed, which means the input is true and the input is true, or rather say current is flowing through and current is flowing through. If I want to say false, current is not flowing through, this current is flowing through, or rather current is not flowing through and current is not flowing through, right? So let's look at the larger circuit. So if current is not flowing and current is not flowing, if input A is off and input B is off, then the output is off. And if input A is on, what do you think the output should be? The output should be off, since it has to meet both conditions. Both of them have to be true for it to be true. And if I turn this off and this on, again, it does not light this up, but only if I turn both on, then this lights up. And essentially that's called an AND gate. And looking at how it works, we can see that current is flowing from here, positive, over here, comes over here. You can choose this path, but this path is open, so there is no path. And it can use this path. Essentially, the current is trying to move from here, positive, to the negative. Notice we're talking about current, not electrons. So, and current is the opposite of voltage. So, yeah. So if okay, for right now, both of them are open. The circuits are open, and we can see the circuit flows, the electrical flows over here, then reaches the first transistor. The first transistor, the base, we say that for a transistor to let current flow, the base has to be activated, but this is not activated. So consider this as a gap. So this is a gap, and also this is a gap. So both of the transistors are what we say they are arranged in series. So this is a gap and this is a gap. That means that electrons cannot flow, and therefore this bulb won't light. And if I close this, we can see that electrons flow over here, they come over here, the base is activated, so this wire is activated. Therefore, the electrons that flow over here, they pass through this, notice that it's the movement of electrons that allows the circuit to the electrical components to work. If the electrons are not moving, then we have nothing. We don't have the electrical charge. So even though the circuit seems to be flowing through this, it doesn't really complete, since we have, right now, this is closed. So electrons flow through here and through here. But when they reach over here to the second transistor, they essentially, since the base is not activated, consider this as a gap. So the circuit is not completed. So the electrons are not going to reach here. That's why this part is grayed out. And even if I interchange like this, it's the same. Electrons flow over here, they come over here, flow over here. Since the base is not activated here, that means that electrons do not flow from this. But electricity uses this other path, and using this path, this transistor is, the base is activated, and therefore this is a complete circuit. But this circuit does not help us, since the LED, or rather the output, is not part of this circuit. So it's kind of ignored. And only if we select both of them is when the circuit electrons are able to flow. The electrical charge is able to flow over here to the first transistor, since the base is activated, and to the second transistor, since the base is activated. And therefore everything is just like the simple basic circuit that we looked at when we were starting. And that's a NOT gate, an AND gate. So for now we have the NOT gate, which inverts the circuit, which inverts the output, inverts the input, and an AND gate, which checks two inputs and compares them, and only if both of them are true, its outputs are true, which in our case is lighting of an LED. And the last circuit we're gonna look at, the last basic logic circuit we're gonna look at is the OR gate. And again, from the word OR, it's like we're looking at two statements and saying we have statement A and statement B, but we're given the condition OR. So if statement A is true and statement B is true, then automatically the whole statement is true. By the whole statement, we mean the output. And if statement A is true and statement B is not true, then still the statement is true, because we're told we just OR. We can choose OR, either of the statement. If one of the statement is true, then the whole statement can be true. And only if both statements are not true, then the statement cannot be true. So let's see how that logical circuit, or rather logic gate, is implemented. So in this case, it's the same. We have two inputs. Right now, both of them are off. By off means that electrical current is not passing through this to activate the base to allow this transistor to act as a normal wire. So if I activate A, so the current can now flow through the first one to light the LED. And if I select B, also the current has this route to flow over here. Since we have activated this other, it can now flow over here, then to this LED. Like, it's kind of has two pads. I can use these and use, but that's a better way to understand it. The other circuit and was arranged in series, which means the electrical current has to flow both through both of the circuits, both of the transistors, for it to reach the LED and it to be true. But for this circuit is arranged in parallel, which means the electrical current is given a choice. You can either choose this route or choose this route. Whichever route is gonna reach my output. So that's essentially all. You're given an option. You can choose either and you're fine. So on this other, you can choose this, and we can now see that the electrical current is able to flow through the second part, and now to the LED. And if again I interchange, it goes through still. And only if both of them are off, it goes off. If both of them are on, still on, because it chooses all of the pads and still the output is okay. It's still the same. So essentially that's how logic gates are. And funny thing, arranging this basically we've seen that the arrangement of this circuit matters in how the thing behaves. And using these simple circuits and the branch of mathematics that our guy George Boole, where is he? George Boole, who invented this, came up with this Boolean algebra. Through all these things, we're able to arrange them and do things that to us they are helpful. They're logical, and the operations that help us is essentially what our minds kind of do. We're able to construct a computer, and a computer is just let's go ahead. So as we said, these logic gates can now be represented in something that we call a truth table. So from here going on, we're gonna use these signs to represent these gates. So this symbol is going to represent a NOT gate or an inverter. Essentially, if it takes a 0, which is off, meaning electrical current does not flow, then the output becomes on. It does the opposite. Yeah, essentially does the opposite of what we tell them to do. And if we tell them to go on, it goes off. That's a NOT gate. And this is called a truth table. And the other kind of gate we have is something called an AND gate that we've just looked at. And it's essentially multiple outputs, in this case 2. And as we have seen, this is the symbol. Essentially, it's like D, and an output. And if both statements are false, becomes false. If one of them is false, becomes false. So for both of these, since one of these is false, it becomes false. And only if both of them are true, then it becomes true. That's the AND gate. You can feel free to look more about it. It's really interesting. And the final logic gate we have is the OR gate. And this OR gate is kind of looks like an AND gate, the D part, but it's kind of curved inwards, and also with multiple inputs. And all of these are just one outputs. And we're gonna look at how that one output is going to represent one bit, or rather one bit, which is a representation of data 1 or 0, and how, again, combining all these things, we can represent everything. And I mean, okay, let me say almost everything that computers can do. So in this case, as we saw, if we have 0 as input and B as 0, we also have 0. If we have both inputs as off, then we have off. And if we have either of the inputs as 1, then it's 1. And if we have both of them as 1, it's 1. Exactly what we have seen. And these are the most basic kinds of representation of gates that helps us construct the computer. We also have other kinds of gates, but these are not the most basic. They are built from these three basic AND, OR, and NOT. They are able to build others. We have NAND, which is not AND. We're gonna look at that probably in our future lessons. And we also have NOR, which is not OR. We also have XOR, which is exclusive OR. We also have XNOR, which is exclusive NOR. I guess we're gonna look at that also. And yeah, so yeah, those are essentially the simple building blocks that are gonna help us build our computer. So the TLDR for this class is we saw that we had this way of representing everything as mathematical concepts, which is done by Boolean algebra. And since this Boolean is either true and false, we happen to have electricity that can be able to represent true or false. We have electrical current that can be able to represent these true and false, and therefore can be able to represent everything we need as stated in Boolean algebra. So it doesn't dictate that Boolean algebra can be implemented on an electrical circuit. You can use anything as long as any representation can be a 1 or a true or a false. you can basically build a computer with it. And it happens to be that electricity does the same. So it's what we use to represent these computation, or rather operations. Let me just call it computer. Yeah, to build a computer and perform everything that we can, and at a much faster way. So I believe this is the end of our lesson, and I'll catch you in the next lesson. Bye.